Okay, so when we were using the sample statistics p hat, right, to estimate the population proportion which was unknown, what we did was we created that plausible region with some confidence in order to find it, right? So we took sample statistics, we created a plausible region with some confidence, and that was called the confidence interval. But because p hat isn't perfect, right? Kind of like in when we were discussing the residuals, some error, right? There's some error between the best fit line and the actual data point observed in chapter 4. Same thing here, p hat is not perfect. There is going to be some error between p hat and the outer bounds. So this piece right here between p hat and the upper region, that's called an error. Okay, that's called E. And then going this way as well, between p hat and the lower bound, this is also called your error E. Okay? So what we try and do in statistics is we try and minimize that error as much as we can. Okay, the less error you have, the more accurate your data will be. So one of the best ways to minimize error is by taking a large sample size. Okay, whatever experiment you're conducting, the larger the sample size, the smaller your error will be. Because the more people, the more units that you sample, the more accurate your information will be. Okay, so in order for us to obtain some sample size, we have a formula. Okay, so this E, if you notice this Z alpha over 2 square root, that we give the notation E. And if you notice, this is going to be the latter part of the confidence interval formula, this piece right here. This is E, P minus E, and then P hat plus E. Okay, we give it a shorthand notation, and that's going to be the error that gets us to the bounds. And if we have an error that we're trying to kind of set as a goal, we're able to calculate how large a sample size should be in order for us to be within some margin of error. And if p hat is known in the problem, we use this formula to find our sample size. If p hat is unknown, we'll use this formula to find the sample size needed in order to be within some margin of error. So I want to look at example 2b that has to do with obtaining a sample size to be within some margin of error. So let p hat be equal to 0.63. What sample size should be obtained to be within 1 percentage point of the true proportion with 90% confidence? So in this problem, we're looking to be within some margin of error. In this case, it says within 1 percentage point. And I do want to point out in the homework assignment, be careful with the margin of error here. This will be your keyword, okay, it's for E, because if you notice in the sample size formula, we do need the margin of error. The way it's worded will be important though. If you see within, okay, that's going to be your error. But what's the margin of error exactly going to be? If you see 1 percentage point, you need to set E equal to 0.01, okay? If, for example, if this was 2 percentage points, E will be 0.02. So percentage we do need to convert, okay? But sometimes a problem will just say, let P hat equal to 0.63. What sample size should be obtained to be within 1 point of the true proportion? Notice that we skipped the percentage part. It just said what size should be obtained to be within 1 point. And if it's phrased in that way, you take the error as is. E is equal to 1. Within 5 points, E is equal to 5. Okay, so if you're looking for the word within, that's going to be what E is equal to. Just be careful. If it says percentage point, convert it. If it doesn't say percentage point, it just says point, take it as is. Okay, so because here we are given the p hat, we're going to use this formula here to estimate the sample size needed to be within 1 percentage point error. Okay, so we need n is equal to p hat 1 minus p hat, and then we need critical value z alpha over 2 divided by the error, and then we square. Okay, so p hat was given. P hat was given as 0.63, so we can plug into the pieces here. E, we need to be within 1 percentage point, so let's call that 0.01. Okay, but I need to find the critical value z alpha over 2. Okay, and recall from the previous videos, to find z alpha over 2, we need inverse norm with alpha over 2, 0, 1. Okay, so in this case, we're still dealing with a 90% confidence. So what would alpha have to be the remainder of the 100%? We would need 0.10 as alpha, but we need alpha divided by 2. Okay, so 0.10 divided by 2, 0, 1. Okay, we've calculated this before. Let's look at it one more time. So here we go to second vars, inverse norm, 0.10 divided by 2, 0, 1. And again, if you want to simplify before, you want to call that 0.05, 0, 1, that's perfectly fine as well. So here we take the positive sign, 1.645, and 3 decimal places is fine when it comes to the critical value. Okay, so we have enough information to estimate the sample size needed to be within 0.01 margin of error. Okay, so we have n is equal to p hat 1 minus p hat, and then we need z alpha over 2 divided by the margin of error, and then we need to square. Is that right? Then we need to square. So let's take the calculator and let's find the estimated sample size needed. So we have 0.63, 1 minus, let's do that again, 0.63. And then here I need 1.645, divide that by 0.01 to the second power, and we get n is equal to 6307.7. 6307.7. Okay. And what you'll notice in the homework assignment will ask you to round. Okay. Now, because it's not possible to take 0.7 of a person, of an object or unit, we're always going to round up. Okay. It doesn't matter what the decimal is. There's rules for rounding. Okay, whether you round up or down. Okay, but with estimating these sample size, even if this was 6307.1.2, we still want to take that piece of the individual unit into consideration. We need to round up in order to do so. So our sample size needed in order to be within 1 percentage point margin of error, sample size must be 6308.